So yeah, hi. Uh, okay, let's start with my introduction. So I'll be presenting a talk on how Postgres can leverage your disk bandwidth to deliver better transactions per second while you're doing writes in Postgres. Okay. So in this talk, what I'll be covering is the background of the problem. Like when I was running the benchmarking, what was the main issue that I observed with the traditional XFS, and then while I was researching, what I found that how can log structure file systems improve this. So I'll be bringing up an introduction of log structure file systems, and then one of the offering which is already available in Linux for this implementation of log structure file systems is F2FS, flash friendly file system. So I'll be explaining the architecture and then basically how I integrated this F2FS with Postgres setup and the benchmarking results, and how did we actually improve our performance using F2FS on a Linux platform using better bandwidth. And in the end, we'll just summarize some of the results, and we'll basically share some benchmarking results. Yeah, so about me, my name is Nikhil, and professionally what I do is I part of performance engineering team, and finding and fixing performance bugs is daily part of work. And apart from work, you can find me on road trips. Yes, okay. So now let's start with the main problem statement. Whenever we do generally write IOs or writes in databases, the main problem is your writes do not identify or associate with each other, because you're writing at table 1 in some point, and then the next point, next instant, you're writing at table 2 at column 2. So therefore, you're sometimes, most of the times in fact, the disk becomes the bottleneck, and you basically use your full churn of your write IOPS on the disk. Yes, and now in this case, why Postgres does random IO? Despite it has higher costs, higher inefficiencies, but yes, why do we do that? So some of the reasons are index scans on unclustered data, high volume updates when we are concurrently using Postgres, and then cold cache. When your database restarted, you're still filling up the buffer, you're still figuring out which is the largest or frequently accessed column. So until you miss that cold cache, you have to still go to the disk and access that part of the data. And small limit or high selectivity queries, basically when you're reading a lot of data which cannot be sustained into the buffer, and nested loop joins. So these are some of the reasons that I identified. Now see, when I ran my pgbench benchmark, you can figure out that while I am increasing the threads and jobs, you see there's a flat line that is becoming, that actually is coming because of your write IOPS basically on the disks. So you're mostly, in this case, the disk is becoming the bottleneck. And that's the graph I'd like to present. That's the telemetry that proves. If you see, there's a flat line also while we are consuming from the IO stats reported, while we are actually using Postgres. When you see the initial bumps, that's because of the checkpointing that happened when I ran the benchmark. And then when your checkpointing has finished, you have flushed the data. The consistent usage of Postgres points that you're basically just thriving on your IOPS. In this case, the disk, which can deliver a 5,000 IOPS, you're mostly using 50% of the IOPS most of the time when you're running your write workload. But at the same time, when the disk can perform 200 Mbps, the disk can deliver 200 Mbps of throughput. But if you see, this is the main problem. You're only using 10% of the disk bandwidth while you're running your write benchmarks. That's where we found the gap. That's what we try to fix, because at any point of time, you cannot increase the disk ability to produce more IOPS. But what you can do is, you can find the already available resources that you can use better. In this case, when I'm running my benchmark, I am still seeing there's a 80% to 90% of gap in the throughput. So that was the whole driving idea of this research and result. Why now? This is the result from an XFS file system based disk. So why XFS is not performant in this case? Why XFS is not judicially able to use these, why Postgres and XFS are not compatible with each other? So what happens is, when you do writes on your system, you send your write, and then basically you use your write IOPS slot, And finally, you just simply at the same time flush your data for consistency. And that's how we are mostly dependent on write IOPS, not on throughput. And since the write IO can be small and large in size, so that is why the average throughput usage is also somehow large, like within 5 to 8% range. It's not flat. So this is now the problem which I have found out, and summarizing this. Now, the answer to this is log structure file systems. Log structure file system, what that does is basically there's a circular buffer. You are bringing your write IO. You're not simply sending that write IO to that disk immediately. Rather than you are giving it some time to just collect it into the buffer, and then the unrelated write IOs now part of the buffer, which are still unrelated but gets flushed to the disk at a certain point of time. And that only gives you the leverage that now previously your write IO, which was of say 8K of size, now you have suppose a buffer of 10 units. So you are now combining your 8K write IOs and into 10 slots, which becomes 80 KB. Now the write that you are going to perform, which the flush you are going to perform, will be of 80 KB in size, which was previously of 8K in size. That is what the leverage is provided by log structured file systems. So that is why you see that whenever you are doing a write in Postgres, the write is not actually happening in place. You are doing it for some time into the memory. And that's the whole write advantage, because now the writes you are going to do will be mostly sequential writes, because now you have find a relationship or established a relationship between these random IOPS. Now, but with every performance trade-off, there's a trade-off here as well. Previously, when Postgres was maintaining most of the consistent state on the disk as well as in the hot cache, in this case, your the latest read will be available into the circular buffer only. And then later you have, suppose if it is not available into the buffer, you have to find it on the disk. So there's definitely a little bit of a disadvantage on this side. But yes, we'll see the metrics that by losing a little bit on read performance, how much you are getting the benefits in terms of write TPS when you are using LFS based file systems. And of course, with the LFS, the other challenge is when you're running LFS, there's a garbage cleaner as well, which has to consistently clean the segments into the memory and then flush the data to the disk. So there's so in a nutshell, basically you're seeing some of the CPU cycles are also getting used. Yes, so this is a log structured file system, looks like structurally wise. And that's an AI generated image. Yes, so in this case, if you see the orange section, that is where our main job that happens. So LFS does your writes in segments. We maintain some in-memory segments. That is actually basically preserving your write IOPS, and then this in-memory buffer is finally gets flushed onto the disk. That is again on the disk also we are maintaining write segments only. Otherwise, for the other thing that this LFS maintains is the inode map. That's for its own maintenance, and segment usage map. That is again an LFS specific concept. Now the other thing that LFS runs is a garbage collection that I mentioned earlier as well. Basically, now you need to constantly clean your data just to preserve your memory and to basically do efficient lookups. Yeah. Now, while I was researching for LFS-based options, like I mentioned, so what I figure out is within Linux kernel itself, you have right now multiple of such options are available right now as we speak, which is BTRFS, ZFS, NILFS, and F2FS. So in my case, why did I use F2FS, flash friendly file system? So the main reason is it is one of the most contributed, and it's a hot file system that is being maintained in Linux kernel. So if you see the patches, there are constantly been happening there on F2FS side. And that's very specific for NAND or SSDs. And you'll be surprised to know right now our Android devices also offers these F2FS. So for example, if you have an Android device, there's a probability that you're running F2FS right now as we speak. So therefore, it was more easy, or I would say more reliable to actually use this one, because it was being maintained in a frequent manner. Yes, so now how did I integrate F2FS in my setup? So you see, what I've created is a table space on top of an, I basically added a disk in my cloud environment, and then formatted that disk with F2FS file system, created a table space on top of that, and finally, now I'm writing the data onto that table. So now the advantage, into the Postgres setup that I was using. You can see there's an F2FS DB, there's an XFS DB. The F2FS DB is using F2FS disk, XFS DB using XFS disk. You can see the specifications here itself, the table space specifications, and your disk specifications. The advantage of this setup is I could actually easily benchmark in XFS and F2FS easily. I could switch between F2FS and XFS easily. So this controls the blast radius if in case if something goes wrong, and of course, ease of benchmarking. Now, while I was running my benchmarking, what options or what basically steps that I took that basically prevented it from adulterating the data. That is basically before every run, I am doing manual vacuum, I'm doing cache drops, and I'm also restarting Postgres just to clear all the FS cache. So there is no adulteration of data in the benchmarking results. I'm also doing making sure that auto vacuum is turned off. Just because if I'm running my benchmark, there is no jitter in that run while the PG bench is executing. Standard I'm maintaining of shared buffers is 25% of memory. That's what we recommend in the community as well. And a wall size of 10 gigs. So basically what happens is having wall size prevents, again, checkpointing also frequently coming into the picture. Again, when you do checkpointing or Postgres is running checkpointing while the runs are happening, that will basically, again, jitter my results. And for observability, sorry, yeah, it's my first. So yes, for observability, I'm using IOStat, MPstat, VMstat, nothing fancy, just these basic metrics only. That helps me to actually connect with these numbers a lot. Now that's the main juice of the whole task. You see, what am I maintaining is I perform 2 benchmarks parallel, like one by one sequentially, and produces some consistent results. Why did I 2 benchmarks? Because to make sure that the results are reproducible consistently. So if you see in the graph, the orange line and the dark blue line of F2FS, the 2 constant runs, and the XFS and the this XFS run 1 and XFS run 2, again 2 constant lines and moving in constant manner only. The result is there's an average peak difference of 63% right TPS right now, and it's very easy. You pick up a setup, make it bare metal or cloud environment. You take a disk, you format the disk with the file system, run your PG bench benchmark. You'll be easily able to replicate these results. Yeah. Now, while am I running my benchmark? My initial topic was how am I using bandwidth here. So you see, when I am running the PG bench benchmark on the same disk, which provides 200 Mbps throughput, maximum capability, my usage of throughput has become prominent. In this case, you see the peaks are crossing more than 50% of disk bandwidth in this case. There are few spikes around 150 MB per second, but the constant usage, if you see, it's 50 to 75 MB per second, which was previously floating only around 20 to 25 MB per second. For reference, I'm again sharing the comparison. You see, the orange line belongs to F2FS, the green line belongs to XFS. The same benchmark, same setup, swapping of disk, and same telemetry collection, same method. But you're using more bandwidth, and the results that you are getting is 63% write TPS are getting better. Now, how did we get to this TPS usage, or how did we were able to perform this sequential IO? Now that's the graph that I'm right now showing is, that's a VMstat graph. Now since your write IOPS are getting preserved onto a circular buffer, so that means there is some usage of memory. When I'm running the benchmark, after resetting the memory, after dropping all the caches, you see the warm-up stage is also happening. In this case, what happens is, F2FS, when it executes, it allocates a buffer, it allocates the segments, and then you start filling in data. And you see there is a minor drop in the memory usage. That is when F2FS flushes happen. Once you have preserved your data enough into the circular buffer, when it's ready to be flushed, there's a flush happens, your memory usage drops, and then again there's a sharp peak. That denotes that you're allocating some memory again, which you're literally which you're going to fill it later. So basically, it's just like you're predicting some data is going to be coming there. So therefore, you do allocations before only, and when the data is there, you simply just go to that offset, fit your right IOPS into the picture. That is why there's a flat usage periodically. When you do flush, you allocate faster. So that means there's a judicious use of RAM also in this case. And now that's the main thing. Again, the write request when it falls on the disk in case of F2FS, in case of XFS, you can see that the write usage, the write request size is floating around 40 to 80 MB per sec, 80 KBs in this case when F2FS is executing. Whereas in case of XFS, there's 8K writes, you are just simply getting the writes and flushing onto the disk. So therefore, the write usage is pretty constant in that case because you're doing in-place writes. Yes, again, the advantage of higher request size, because when you're flushing again, that gives the bandwidth boost. Again, I'm pointing the same graph. I'm just trying to connect my dots here. The higher the request size, the higher the bandwidth usage. And that's the right IOPS pattern in this case as well. So why do you see like a sawtooth pattern is basically XFS has allocated segments into your memory. Now you're filling up the data into the segments. Some of the segments become unavailable, therefore the write rejections happens. And then once you have basically churned out all the segments into the memory, you do the flush. That is where your valley is. Again, you allocate the data or allocate new segments. That is why the sawtooth pattern that you see on IOPS side is being preserved. Also, you see for the same clients that I was using for the test, for 80 cross 80, XFS was using the IOPS also around 2000 to 2500 in average range. But in this case, the constant IO usage is more than 3000 IOPS for the same workload. And for, again, you're using better IOPS and you're getting 63% of better write performance at the same time. But yes, performance always comes at a price. The price is in this case the CPU usage. While I was running the benchmark using XFS, the CPU usage was 40%. You can see that's a CPU idle percentage graph, which means your CPU is being used around 40%. But the blue line of F2FS denotes around 20% CPU is idle. That means 80% of the CPU is being consumed here constantly. Why that CPU is being consumed? You see, when you install F2FS into your system, there are multiple F2FS kernel threads, multiple F2FS related processes are running. Checkpointing, flushing the data. Now this checkpointing is very much relevant to the checkpointing that in PG happens. You write to the data to the wall, eventually you have to flush the data. Same principle that F2FS also follows. You have to write into the buffer, you have to flush the buffer. And then basically there's a garbage cleaner. Again, if you need to compare with Postgres, there's an auto vacuum process that runs and cleans your transaction IDs, right? The same that happens here as well. A garbage cleaner cleans your segments. So that is why your CPU cycles are being consumed. So am I going fast? Okay, so now to summarize everything, so basically, what do you get? When I was running the XFS workflow, I was generating the baselines, but what am I getting is 63% better sequential write patterns. Why? Because I have a larger write request, I'm flushing the larger data, I can now connect my write request into one large request. Therefore, consistency, of course, now that's where the negatives of F2FS come into the picture. Because XFS is doing in-place writes, you are not preserving anything into the memory. So suppose in this case, if power loss happens, your write request was there into the disk, so there's no risk. But in case of F2FS, you see some of the data is being preserved into the memory first, so that a larger write request can be formed, the circular buffer. So therefore, if those write requests are in the memory and you do a restart or you do basically reboot of the machine, an abrupt reboot, so you may lose on those writes. In case of cold start recovery, it's pretty faster to read LFS, like for LFS to read the data, because it's because of the ability of LFS, the architecture that LFS offers. The vacuum throughput, in this case, like for XFS, I'm comparing the baseline of 20 to 25 MB per second. But here, I'm definitely getting a double in an average. Because what we are doing is, we are just simply doing append-only operations. Your write request comes, you append the data, forget. F2FS will take care of the data later. But in case now the maintenance part. F2FS has a little bit of higher maintenance because it storms the disks with IO, it storms the disk with larger request sizes. And then when you have larger concurrent operations that are happening, you need to do cleaner actions also faster. That is why there was a high CPU usage as well. So in this case, what happens is, generally, in my benchmarking, what I've seen is, I'm mostly running out of the CPU first than getting out of the disk first. In general benchmarks compared to XFS, when I'm running a higher benchmark, increasing clients more and more. So what I've seen is, I am basically touching the disks, what the disk can provide, and the disk becomes the bottleneck because of the random IOPS. But in this case, if you keep on scaling, you'll first touch the CPU bottleneck first. We have already seen in the results already that the CPU usage is constantly higher. Yes. Now, as I mentioned, the trade-offs. There's one major trade-off is which I already mentioned, that the data loss happens when when there is an abrupt process restart, or there's an abrupt power failure. So in this case, I've also mentioned some remedies that can be used. In this case, a battery back RAM. Suppose if there's a power loss, the battery back RAM has the ability that it can flush the data onto the disk before actually getting shut off. Or also, we can tune F2FS to do checkpointing. This checkpointing is as same as that you do in PG as well. So if you do faster checkpointing, again, you may lose on CPU, but yes, you'll be able to preserve your data in this case. The checkpointing also, now there are certain more F2FS tunables. I could not cover most of these topics for this talk because it would have become a lot of knowledge in one talk itself. So there are few F2FS tunables are also available. There's a garbage collection overhead when you're doing high churn of IO. So that means the garbage collection also becomes aggressive at the same time. So therefore there's a GC overhead as well. And there is a write metadata amplification as well, because F2FS again has to preserve the data. It has to update multiple tables. Segment, there's something called SIG, segment, sorry, I can't recall the name. And there's a node address table, and there's a segment table, segment metadata table that F2FS preserves. So therefore, there's a write amplification factor that comes into the picture. But still, again, at the same time, I'm showcasing again that you're getting 63% of the benefits with all these trade-offs. Yes, in a nutshell, I'll say that F2FS is a speedier, fast-track F1 car, but it requires a little bit of maintenance. But yes, that's the same for everywhere. Yes, that's the end of the talk. Sorry. Yeah, so that's the end of the slide. We'd like to showcase in the end that there's a Microsoft event for Postgres community that's called POSET. That's going to happen on June 16 to 18. That's a virtual developer event only showcasing Postgres studies and topics from Postgres. So please register and visit. So.